Imagine this. You're gazing at the night sky, and suddenly, the stars begin to shift in ways that defy explanation. What if, lurking just 1 light-year away from Earth, a distance that's a cosmic stone's throw, an enormous supermassive black hole appeared? Would it swallow our planet whole? Disrupt our solar system? Or, nothing at all? Today, we're diving deep into this mind-bending hypothetical. We'll explore the science from every angle: gravity, radiation, long-term fates, and even some wild edge cases. Buckle up. This is What If a Supermassive Black Hole Was Just 1 Light-Year Away from Earth? Let's break it down step by step. To grasp what could happen, we first need to understand black holes. These aren't just sci-fi villains. They're real cosmic phenomena predicted by Einstein's general relativity over a century ago. A black hole forms when a massive object collapses under its own gravity to a point of infinite density called a singularity, surrounded by an event horizon, the point of no return, where escape velocity exceeds the speed of light. Black holes come in varieties. Stellar mass black holes, born from dying stars 20+ times the Sun's mass, weigh 3 to 100 solar masses and span a few kilometers across. Then there are intermediate ones, hundreds to thousands of solar masses. But for this scenario, we're talking supermassive black holes, SNDHS, behemoths with millions to billions of solar masses lurking at galaxy centers. Take Sagittarius, a star, SGR, A star. The SMBH at our Milky Way's heart, about 4 million solar masses, with an event horizon roughly 24 million kilometers wide, twice Mercury's orbit around the Sun. It's 26,000 light-years away, influencing our galaxy's structure, but posing no threat to us. The nearest known black hole, Gaia BH1, is a stellar mass 1 at 1,560 light-years, quietly orbiting a star. Historically, black holes were theoretical until 1971's Cygnus X1 confirmation. Today, we've imaged Sagittarius A star and M87's black hole via the Event Horizon Telescope. They're not sucking everything in like vacuums. Their gravity acts like any massive objects, just intensely close up. If the Sun became a black hole, it won't, too small. Earth's orbit wouldn't change. We'd just freeze in darkness. Nuances: active S, MBHS, like quasars, accrete matter, emitting jets and radiation brighter than entire galaxies. Quiescent ones, like SGRA star, are dormant. In our hypothetical, we'll assume a quiescent SGRA star like SMBH at 1 light-year, 4 million solar masses, to start, then explore variations. 1 light-year sounds close, but let's contextualize. A light-year is the distance light travels in a year, about 9.46 trillion kilometers, or 63,240 astronomical units, AU Earth-Sun distance. The Moon is 1.3 light-seconds away. Pluto averages 5.5 light-hours. The Oort Cloud, our solar system's edge, extends to 1 to 2 light-years. Proxima Centauri, the nearest star, is 4.2 light-years away. So, 1 light-year places this SMBH inside our solar system's extended bubble, beyond the heliosphere but closer than any star. Astronomically, it's intimate. In human terms, unimaginable. Implications: light and gravitational changes, from there, takes a year to reach us. If the black hole appears suddenly, pure hypothesis, physics doesn't allow it, we detect it optically after 365 days, but gravitational effects propagate at light speed too. In reality, SMBHS don't teleport. No, they'd approach over eons, perhaps ejected from galaxy mergers. Edge case: if wandering at high speed, SMBHs can reach 5,000 kilometers per second post-merger, it could zip by quickly. But we'll assume it's stationary relative to us for simplicity. Transition: Equations on screen, animations of gravitational fields. Section 3. Gravitational effects on the solar system. Now, the big question: what happens gravitationally? Gravity follows Newton's inverse square law, refined by relativity. Force equals G times m 1 times m 2 over r squared. For acceleration on Earth, or the Sun, A equals G times m bh over d squared. Plugging in, MAU-BH equals 4 million solar masses, 7.956 times 10 to the power of 36 kilograms. D equals 1 light-year, 9.46 times 10 to the power of 15 meters. G equals 6.674 times 10 to the power of minus 11 meters, cubed kilograms to the power of minus 1 second to the power of minus 2. Calculation yields approximately 5.93 times 10 to the power of minus 6 meters per second squared. Tiny! For comparison, the Sun's pull on Earth is 0.006 meters per second squared, 1,000 times stronger, and Earth's surface gravity is 9.8 meters per second squared. So, no immediate yanking. The pull is uniform across our solar system. Diameter approximately 100 astronomical units, or 1.5 times 10 to the power of 13 meters, 0.0016% of 1 light-year. Tidal forces, which stretch objects, like moon's tides on Earth, are delta A approximately G times mbh over d cubed, times diameter approximately 9.4 times 10 to the power of. Instead, the entire solar system feels a gentle tug toward the black hole. Over a year, velocity change is approximately 187 meters per second, 0.006% of Earth's orbital speed, 30 kilometers per second. But cumulatively, we'd accelerate toward it. If stable, the Sun and planets could enter a circular orbit around the black hole at 1 light-year. Orbital velocity v equals square root of g times m sub bh over d, approximately 237 kilometers per second, similar to our galactic speed. Period t equals 2 pi square root of d cubed over g times m sub bh, approximately 8,000 years. Our solar system becomes a planet, orbiting this new giant. Short-term, minimal disruption. Oort Cloud comets might perturb slightly, increasing comet activity over centuries, but no apocalypse. Planets stay bound to the Sun as the black hole's heliosphere, influence radius, encompasses us all uniformly. Nuances. Relativity adds gravitational waves if accelerating, but minor. If the black hole moves toward us at, say, 100 kilometers per second, closing time is approximately 30,000 years, plenty for gradual shifts. Edge cases. If more massive, 30 billion solar masses, like the ultramassive one in Abell 1201, acceleration scales up 7,500 times to approximately 0.044 meters per second squared, stronger than suns on outer planets, potentially ejecting Neptune/Pluto quickly. If stellar mass, 10 solar masses, effects drop to near zero. Gravity isn't everything. If active, like a quasar, accreting gas forms a hot disk, emitting 10 to the power of 40 watts, 100 billion suns worth. At 1 light-year, flux approximately 9 million watts per square meter, 6,500 times Earth's solar constant, 1,366 watts per square meter. Earth would roast. Dayside temperatures could hit 1,000 degrees Celsius, boiling oceans in weeks. Radiation, X-rays, gamma rays, strips atmosphere, sterilizes life. But Sagittarius. A star is quiescent, flaring mildly. Visibility. Without accretion, it's invisible. No light escapes. We detect it via gravitational lensing, bending starlight, or star orbits. First sign: aberrant proper motions in nearby stars after a year. Jets. Active SMBHS. Shoot relativistic particles. If aimed at us, high-energy cosmic rays spike, but at 1 light-year, diluted by inverse square. Implications: human detection via telescopes like JWST, spotting lensed light. No immediate panic, but long-term climate shifts if radiation warms space subtly. Over millennia, orbiting the black hole, our night sky changes. Stars whirl faster. Galactic context. We drift from the Milky Way, potentially merging with Andromeda earlier, in 4 billion years anyway. What if closer? At 1,000 astronomical units, 0.000016 light-years, acceleration approximately 0.37 meters per second squared, disrupts outer planets. At 1 astronomical unit, approximately 2.4 times 10 to the 8th meters per second squared, spaghettifies Earth instantly, tides ripping atoms apart before event horizon. Schwarzschild radius for 4 MSMBH, approximately 12 million kilometers, or 0.08 astronomical units. If flying by at light speed, impossible for mass but hypothetical, brief intense gravity warps space, but no collision. Broader implications, challenges galaxy formation theories. How did an SMBH get here? Could seed new mini-galaxy? Ethically, no real threat, but reminds us of cosmic fragility. Closing scene. Fade to Earth from space. Inspirational music. Narrator. So if a supermassive black hole parked 1 light-year away? Surprisingly, not much chaos. Our solar system hitches a ride in a new orbit. But tweak the details, make it active or closer, and it's game over. This hypothetical highlights gravity's subtlety, black holes' diversity, and our universe's vast scales. What do you think? Terrifying or fascinating? Drop your thoughts below, suggest next scenarios, and hit subscribe for more cosmic what-ifs. Thanks for watching. See you in the stars.